We will start the seminar now, and I'm very pleased to welcome Wojciech Zurek. And I think I will present him in English because he has been subjected to a long French discourse, and I think it's better for him to get used to speaking English again before he starts. So Wojciech has started his studies in Krakow in Poland, and then he went for his PhD in Austin in Texas. And after his PhD, he became a postdoc for Wheeler, with whom he get acquainted with the fundamental questions about quantum physics. And I remember that he edited with Wheeler a famous book about quantum measurement, which was correspondent, I think, to a conference which took place at the beginning of the 1980s and which end of the 70s. Collection of papers which discussed the fundamental aspects of quantum physics, and which has become a Bible for all the people interested after that in quantum information. Wojciech is a theorist, and he has contributed to a lot of interesting problems, not only connected with quantum information. In fact, he's known for the Zurek-Router theorem, which says that it's impossible to clone an unknown quantum state, and this has, of course, very deep consequences to the meaning of the wave function. It means that you cannot reconstruct the wave function of a system if you have only one copy of it, because if you were able to clone, you could make an arbitrary number of copies, and then the wave function would have a meaning quite different from what it has in quantum information. And in one of my lecture series a few years ago, I discussed cloning in details, and on that occasion I talked about that. Another great contribution is known as the Kibble-Zurek mechanism, where you study the formation of defects in a system which undergoes a second-order phase transition. And when you vary the speed at which you cross the phase transition point, and this has a lot of applications to astrophysics, to nuclear physics, and now to cold atom physics. And we have people here in the group of Jean Dalibard who have been studying this mechanism, and you will certainly be interested in visiting there. Now, the reason why we have been very much interested in Wojciech's work is connected, of course, to the problem of decoherence. And I remember that I read for the first time your famous paper in Physics Today in 1991, in which you describe in very simple and clear terms the decoherence of a harmonic oscillator in a superposition of two states having opposite phases, the famous Schrödinger cat problem. And I must say that we realized at that point that we had the experimental system which would allow us to observe this and to observe decoherence. And of course, there is much more than that to decoherence. We have to understand the role of environment. You have to understand what a measurement really means, what happens when you couple a system to a measuring device. And I think these are all the problems that you will address during these lectures. In particular, this idea, this metaphor that you can relate the problem of quantum coherence and decoherence to Darwinism and to the fact that some states are better to resist to the effect of environment than others. So I'm sure that you will describe this idea, and that you have also been interested in the foundation of quantum physics and the necessity or not necessity to use the Born rule as a principle or as a deduced fact. And I'm sure that you will be discussing that. So we are very eager to attend your lectures, and I remind the audience that there is one lecture today, and there will be another lecture next Tuesday. And I give you the floor.
Thank you. Thank you, Serge, for very kind introduction, and thank you for the invitation and for the opportunity to address this audience. The theme that I shall discuss is the relation between quantum theory, which is an overarching physical theory. It touches on everything. We've just seen in Serge's talk that with exquisite accuracy it predicts whole range of phenomena, and it goes beyond what Serge discussed. I mean, DNA, condensed matter physics, iPhones, that would be all unimaginable without quantum physics. And yet, in spite of that success, there is a fundamental discomfort which has to do with the relation between quantum physics and our everyday world. So this is the theme. How do we reconcile quantum theory with our experience? The plan is going to be, in lecture 1, start with a summary of decoherence and environment-induced superselection, or einselection for short. And to go into foundations, understand how many of the textbook axioms listed in beginnings of texts of quantum theory are really necessary. And in particular, I shall endeavor to derive what I think is a key ingredient to quantum jumps, or perhaps even collapse of the wave packet. And I shall talk about the origins of probability, Born's rule, how does it follow, I believe, from entanglement. In the second lecture, I shall go on to discuss quantum Darwinism, the origins of objective reality. In a sense, the theme of both lectures, while they are based and will start from the foundations of decoherence, will be to go beyond decoherence and understand things in the first lecture more deeply, and in the second lecture beyond. By the way, in case if I miss, and I'm sure I won't do everything I'm planning, there are 2 papers which are, I think, accessible, which cover more or less the same ground as my lectures. So, what is the problem with the correspondence between quantum theory and our everyday reality? Let me start with a quote. This is a letter written by Albert Einstein to Max Born a year before Einstein died. He says, let psi1 and psi2 be 2 solutions of the same Schrödinger equation. When the system is a macro system, a bottle of Coca-Cola, and when psi1 and psi2 are narrow with respect to position, bottle of Coca-Cola, which is here, then in by far greater number of cases, this is no longer true for the superposition. So bottle of Coke here and bottle of Coke there is not narrow. So narrowness with respect to macro coordinates is not only independent of the principles of quantum mechanics, but is moreover incompatible with them. In other words, quantum theory says states like this, superpositions, are to be treated on equal footing as states which are localized. But states like this are delocalized. They do not correspond to our perception. So whatever we perceive is not just independent, but incompatible with quantum mechanics. And we know, and here I am, I think, stealing graphics from one of the presentations of Serge from a few years ago, that there are ways, this is the one famous one due to Schrödinger, of putting systems which are large in superpositions which are uncomfortable, the sort that made Einstein uncomfortable. One good quote demands another. So here's another good quote. Space is big, really big. You just won't believe how hugely, mind-bogglingly big it is. Who can tell me where does it come from? You must have heard my talk before. Yes. Okay, then we share favorite books. Hitchhiker's Guide to the Galaxy. I am going to supplement it with one single word. Hilbert space is big. It's just huge. This is this huge quantum space of all possibilities. Every superposition of every superposition is a legal state. The sorts of states that Einstein was uncomfortable with. Somehow, within this huge space of all quantum possibilities, we need to understand the origin of the classical corner, the sorts of states we perceive on a daily basis. How does all this freedom become constrained? Now, how do textbooks deal with it? And when I mean textbooks, I mean a good textbook. In fact, it is still my favorite. I've extracted from it a sequence of postulates. We start with two which are beyond question. States live in Hilbert spaces. The physical import of it is quantum superposition principle, precisely what Einstein worried about. Any superposition of any superposition is good enough, or is as good as anything else. Second, evolutions are unitary, generated by Schrödinger equation. Unitarity means, in particular, linearity. If you start with a superposition of two things, the evolution will give you a superposition of evolved ingredients. This is why Schrödinger cat comes out in Schrödinger's cat experiment. In a sense, 90%, probably 100% until quantum information came about, of calculations which were done using these two principles. But at this point, we are doing only mathematics. We are shuffling symbols. There is absolutely no connection with physics. So to make connection with physics, one needs more. And Dirac provides more. The next one, and I've signaled a change of theme with a different color, connects whatever symbols are with measurements. Immediate repetition of a measurement yields the same outcome. This is known as repeatability. One could, and I will occasionally call it predictability, because it's really the same thing. In a sense, well, it is a postulate which theorists love, and we think it's essential. Because what can be more essential for the idea of a state as means of prediction as the possibility of verifying that the system is in a state in which it is? Experimentalists know extremely well that making measurements of the sort which verify this postulate is extremely difficult, and one of the most beautiful ones was done at École Normale Supérieure in the sort of microwave cavities that Serge described just before. I like these postulates. They are still in blue. The next one is in red, for good reason. It's a collapse postulate. I split it into two pieces. Outcomes of measurements are restricted to orthonormal states, eigenstates of the measured observable. This comes out of blue. It's not clear why. B, just one outcome is seen each time. This is inconsistent with the linearity of postulate 2. If you have a superposition of possibilities which should come out, how come just one pops up? The next postulate is known as Born's rule. If you have outcomes which are coming out, the probability of finding a specific outcome, a system in an outcome state, Sk, is given by the amplitude squared. Right? We all know that. I'm going to supplement this list with one more. If you have a system which consists of several quantum pieces, it lives in a Hilbert space which is a tensor product of constituent Hilbert spaces. Entanglement is allowed by postulate 0. It actually doesn't appear in Dirac because he didn't worry about it, but whenever you look at things about quantum information, it is essential because different qubits abide by it. So, I emphasize again, the top of the list, 0 through 2 are only math, just mathematics, shuffling symbols. We are beginning to touch on connection with physics with number 3. In a sense, my task will be to try to show you that 4 and 5 aren't necessary. I will succeed at least partially, but we'll be the judge of that after the end of the talk. Of course, forefathers of quantum theory realize there is a problem. There is a glaring inconsistency between unitarity and superpositions and collapse. So, Copenhagen interpretation was invented. It said universe must consist of 2 domains, classical and quantum, and interpretation of quantum mechanics without anchoring it in a classical domain is impossible. And weird things can happen on the border between quantum and classical, so you can have this list. That's not very satisfying. In particular, we know that things like classical apparatus are really made out of quantum stuff, atoms. So quantum mechanics should be allowed to shed light on what happens during measurements. And this is going to be, in a sense, a theme of what we are doing. There is another way of looking at things, at interpreting quantum mechanics. It's due to Hugh Everett. It relies on the fact that there are relative states. In other words, if I am in a state, and this I here is I, who have detected result number 17, then the rest of the universe with respect to me is in a state corresponding to me having detected number 17. That's great. It does not call for classicality, but it leaves a lot of questions open. In particular, you need a preferred basis. It leaves open the original question of Einstein, which pops up throughout this list, for example, in 4a. Why are states restricted to? What makes that restriction necessary? So that question, preferred basis, is actually answered by decoherence. I don't disagree with the answer. I will later point out that the ingredients one uses for the answer depend on the red part of the list of the previous transparency. But let's summarize decoherence. Let us remind ourselves, what does it do? So what decoherence says is that systems exist immersed in the environment. And in particular, large systems are impossible to separate out of environment. That makes their evolutions different. That alters the applicability of the quantum postulates. Why? Because if you start a system, and here is S with some initial state psi as superposition of some state sigma, and let it interact with the initial state of the environment, typically, even if they are initially not entangled, they will entangle. So you will have some sort of entangled state of the system and the environment. So you have one big state which describes both. Now, if you are interested, as we often are, just in the state of the system, then you have to take a trace over the environment, and this will give you so-called reduced density matrix. It's an object which has the same physical interpretation as probability distribution. These are probabilities of finding the system in this set of states. The fact that you can use them and that they are useful goes back to Landau and von Neumann, late 1920s, early 1930s. What has not been appreciated until the work on decoherence, last 30 plus years or so, is that when you start the system almost in any initial state and the environment in almost any initial state, at the end, on the diagonal of the density matrix, there will be the same set of states. So there is something very special about these states. And in particular, if you started your system in one of them, it would not change at all. It would not entangle with the environment at all. So there are these special states which have the ability to survive the environment. These special states are selected by a process which I call environment-induced superselection, or for short, Einselection, and I call them pointer states because pointer of the apparatus has to be in a definite state. But they emerge purely from the interaction between the system and the Hamiltonian, and in particular, the interaction Hamiltonian has key deciding power of which states survive intact. And in simple situations, these pointer states are selected simply because they commute, or observables which are diagonal in them commute with the interaction Hamiltonian. Now, this is the overview of a story which has been known on for a while. I emphasize here two points which will haunt us, which is that we are taking a trace over the environment, and what one does when one takes a trace is actually one averages over. Now, averaging over means you're appealing to probabilities, and probabilities sneak in at this stage via Born's rule. So at some point when we go after a derivation of Born's rule, we shall not be able to use tools of decoherence. And at this point, interpretation of density matrix as a physical object is dependent on accepting Born's rule, one of the postulates. I mean, we know, we love it, verified. But it sticks out like something that should be derivable from the rest of the mathematics. Okay, to go for a very specific system, simple example, let me think of a qubit, a superposition of up and down, 0 and 1. If it couples to the environment through an operator, through a Hamiltonian, which is diagonal in 0, 0, 1, 1 basis, the density matrix, which corresponds to this initial pure state, so this is pure state density matrix, will evolve into something which is approximately equal to only diagonal terms in 0, 0, 1, 1 basis, and off-diagonal terms gone to 0. Einselection, this interaction selected preferred states, 0 and 1. In cases which are more complicated, you can go through a more sophisticated procedure. Basically, you look at every state in the Hilbert space and see if it remains pure or not after you've let it interact with the environment for a suitable amount of time. Here, I am evaluating the purity of the final state by calculating trace rho square, which is called purity. You can do trace rho log rho, which is von Neumann entropy, and generally when you do that, you will end up with a subset of states, the peak of purity in this case, which would be candidates for classicality. Now, this is a very bad picture in the sense that I'm trying to give you an image of Hilbert space, which is very many dimensional and two-dimensional screen, right? But the idea is simple. There is a set of preferred states. Qubit is not a very good candidate for a classical system, so let's look at something which is more classically representable. Harmonic oscillator. So here is a ball rolling in a harmonic potential. It's my harmonic oscillator. The environment is a field. It doesn't matter. The algebra is essentially the same. It's a harmonic oscillator coupled to a bunch of harmonic oscillators. The only important part to notice about the coupling is that it is proportional to the coordinate x of this harmonic oscillator. Don't worry about this. It is coupling to the environment. One can solve this problem because it's linear exactly, trace out over the environment, and obtain effective equations of motion for the motion of the oscillator alone. I know this looks dense. I shall not dwell on it too much. I shall just give you the basics of physics. The first term, so as I said before, this is going to be for a density matrix of the harmonic oscillator. The first term is so-called von Neumann equation, commutator of the Hamiltonian with the density matrix. It is a Schrödinger equation written for the density matrix. The second term is responsible for relaxation and damping, but if you were to look for a limit, classical limit of quantum mechanics, just as a mathematician, you would pay special attention to the last term. And the reason for that is that if you think classical, you think Planck constant h bar becomes small. Now, when Planck constant becomes small, this term blows up fastest. So if this term blows up fastest, let's ignore these two for the time being, and let's look what happens. If this term blows up fastest, the pieces where x is equal to x prime on the diagonal of the density matrix will not be affected. But whenever x is not equal to x prime, there is going to be exponential suppression. So if you look at a state which could come out of a double slit experiment, the sort of state Einstein worried about, a superposition of here and there, the density matrix before decoherence would have 4 peaks, 2 of them on the diagonal, corresponding to possible locations of the bottle of Coke, 2 of them away from the diagonal. It's a pure state, so these 2 peaks record the coherence between whatever's on the diagonal. If you let decoherence have its way with it for a bit, this is what happens. Peaks on the diagonal are essentially untouched. Peaks away from the diagonal shrink. How quickly does it happen? Well, let's look at numbers. Same example. Turns out in quantum Brownian motion, you can connect the rate at which momentum or energy is lost from the system, so it's a damping constant gamma, to the decoherence rate. Decoherence rate is proportional to gamma. So you would think, I make gamma very small, I make the energy loss from the system very slow, isolate the system extremely well, and I'm done. I have suppressed decoherence. Well, in the macroscopic domain, it's not so easy. Let us take a very specific example. Separation of 1 centimeter, macroscopic but not huge, mass of 1 gram, and temperature, room temperature. The reason we need this is because this gamma is multiplied by the distance between the 2 peaks expressed in units of thermal de Broglie wavelengths. Quantity squared. If you plug these numbers, 1 centimeter, 1 gram, room temperature, this factor turns out to be 10 to the power 40. So if you have isolated your system so that gamma corresponds to loss of energy on a time scale equal to the age of the universe, 10 to the 17 seconds, Hubble time, you will lose coherence on a time scale of 10 to the minus 23rd second. Very fast. That's why quantum computing is so difficult. By the way, experiments which confirmed it were done first here at École Normale, and Serge and I see Michel Brun, who were successful in verifying the basic tenets of this. Since then, experiments were done in many other places, beautiful experiments in Vienna with fullerenes, etc. Okay, so let me summarize what does decoherence do. The thesis was, quantum theory can explain emergence of the classical. Put it differently, it will suppress symptoms of quantumness. It restricts the states which are stable in presence of the environment to the exceptional pointer states that somehow manage to survive immersion in the environment. Predictability sieve can be used to sift through the Hilbert space of any open system. That's the strategy of finding states which survive best. And environment-induced superselection is a process of selection of preferred states. For macroscopic systems, ion selection can be extremely effective. It will choose, by the way, in the example with harmonic oscillators, states which are localized both in position and momentum. And we haven't really touched the story of interpretation of quantum mechanics, and we're going to stay away from it. But just to make a connection, in the context of Bohr's theory, one could say that things which decohere are effectively classical, things which do not decohere are quantum. One could also say, in Everett's language, that branches are designated, labeled by preferred pointer states. Now, I am going to switch gears after this transparency, so if there are any urgent questions, ask them now. I'm happy to entertain them. And take a drink in the meantime. If they are not, let's proceed. So this is a nice theory. Why don't we like it? Well, the whole apparatus depends on Born's rule. So it depends on the postulates which I have, for the purpose, listed in red. Why does it depend on Born's rule? Because tracing is averaging, so a physical interpretation of reduced density matrix as an object with moral right to represent quantum states as if this was classical probability distribution depends on a postulate we do not want to use if we want to eventually end up by deriving it, because that would be circular. So from now on, we will need to do things differently, and we should question whatever we've derived, including pointer states. So if we want to talk about the probabilities, we should come up with another way of deriving states which are special. This is going to be our first aim. In other words, from now on, my credo is 0 through 3. Hilbert spaces are composite. States live in a Hilbert space. evolutions are unitary, and immediate repetition of a measurement yields the same outcome. There should be a way within quantum mechanics to do that. So how do I proceed? First, why are measurement outcomes limited to an orthogonal subset of possible states? In other words, where do events come from? Second, Bohr's rule. That's a plan for the next half an hour or so. Cannot use Bohr's rule, cannot use decoherence until we derive Bohr's rule. So our hands are tied to that extent. We start with number one. Why are measurement outcomes limited to orthogonal subset of all the states? Turns out, and this is a derivation. Derivations are not supposed to be served during colloquial-like settings, but I shall make an exception, and I hope you will stay with me, okay? So I want to derive, well, let me just do it. What I imagine is a quantum system, and I'm thinking of two states of that quantum system, state U and a state V. And I also have a quantum apparatus. It starts in a state A0. This is measurement. It will be unitary. It has to be unitary evolution, right? I believe in my credo. So the measurement is supposed to change the state of the apparatus from A0 to something that is correlated with AU, with a state U. And similarly, state V is supposed to be changed from A0 to something which is correlated with V. Here's, I think I have about 20 minutes. I can take more, okay. So, sorry? Within reason, okay, within reasonable, so that gives me something to think. So let me do a sort of medium length derivation. This is key, right? This equation assures me of repeatability because if there is another apparatus that I have stored in my lab in a state A0, same interaction, I would have, you know, U A0, A0 going to U, AU, A0 going to U, AU, AU, right? Repeatability. Same with V, right? So if the state of the system stays put, I have repeatability. So if I have repeatability, and if I've achieved it by unitarity, that means that I can take a scalar product of the left-hand sides. Scalar product of the left-hand side is just a cosine of an angle in the Hilbert space, and by unitarity, it has to be the same as the scalar product of the right-hand side. This is a crucial step. So if you do not believe me, question me now, because it will be too late later. I presume you believe me. Okay, so if you believe me, I'm going to write it out in gory detail, right? I skip the middle lines. It's for the longer derivations that would take a few minutes, and I don't want to go into it, right? So I took a scalar product of this thing with itself and this thing with itself. I have UV A0, A0. A0, A0 is 1, right? It's the same thing. UV, AU, AV. It's a trivially simple equation with grave consequences. Now, if you see an equation like this, an obvious temptation is to do this, simplify. But if you simplify, you have proved that a measurement hasn't happened. Why? A0, A0 is 1. Therefore, AU, AV has to be 1. If AU, AV is 1, that means AU is the same as AV. That means there is no distinction in the state of the apparatus which was supposed to be correlated either with U or V. Measurement hasn't happened. Horrible. We've proved from the credo that measurements are impossible. Or maybe we made an algebra mistake. Well, actually, we did make an algebra mistake. Scratching out was too hurried. The other possibility is that it cannot be possible to divide by the scalar product of U and V. And the reason it may be impossible is because U and V are orthogonal. The product is 0. When the product is 0, in other words, it's the only possibility in which you can make measurements which are repeatable. This is important, right? We've proved something about restrictions to possible outcomes from extremely minimal assumptions with very straightforward reasoning. Reasoning, by the way, which is in some ways reminiscent to no-cloning theorem. So, I was sort of annoyed with myself that I discovered it quarter century after I've understood no-cloning. Any questions at this point about math? Please.
We talk about the reflectibility of one kind of measurement.
Yes. Yes.
Why do I need two orthogonal states to argue for that? I should not worry about whether this state is embedded in a space where it also provides orthogonal states or not.
When you are going to make a measurement, you are going to measure something. So you presumably will have a menu of outcomes. So you will need to specify positions on the menu corresponding to other outcomes. So this is a restriction on the set of outcomes in the menu of a measurement. I didn't say hermeticity, it came out of the blue. You look both puzzled and convinced. So this is a superposition state. I think you will collapse.
Continue afterwards, but I mean, I could consider the state U
Yes.
as a set of orthogonal states where your logic applies. The set of V in another set of logic
Absolutely.
in the same space, which are not orthogonal.
Absolutely.
In case I have repeatability.
Absolutely. 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 So let me emphasize something which is crucial. This evolution has to be the same. I cannot change the rules depending on the state. If I change the rules depending on the state, I'm going to have to change the whole rest of the menu. Right? So in other words, the nature of the evolution selects the state, the set of states which are repeatable. You're welcome to iterate later, but this is, simple and I would very much like to convey it. Okay, so we have a set of preferred outcomes. We have a set of states which are orthogonal, and repeatability, unitarity, etc. The quantum credo gave it to us. We don't need anything more. QED. What does it give us? Predictability implies restriction to orthogonal states. Discreteness behind quantum jumps. If a system is to keep on making records of its state in the environment or in the radiation field, the states which are being recorded many times have to be orthogonal. A case of collapse, because you have a set of preferred states, it does not give you a single outcome, right? We have unitarity, which means all the possibilities are to be respected. but there is a restriction to the set of possibilities. So quantum measurements are multiple choice, and the choices are specified by the apparatus you build. It specifies this evolution, and once you know that evolution, you have a set of states. Consequences and extensions. Derivation of quantum jumps. The key to collapse postulate. 4a, it was numbered there. This already precludes being able to find out what the state is, right? If you want to find it out in measurement, which you can reconfirm, this already makes it impossible. It implies observables are Hermitian, which is what Dirac says. Why are they Hermitian? Observables which have orthogonal eigenstates are Hermitian, end of story. Proof similar to no cloning. It can be extended to when the apparatus or the environment is initially in a mixed case. Algebra is tougher, but basic ideas survive. As well as to mixed decohering systems. So my system didn't have to be isolated. It could have been mixed and decohering. The conclusion would be there that the outcomes would have to live in orthogonal subspaces of the Hilbert space of the system. Predictability or repeatability was key to the proof. If you let the state change, the proof doesn't work. And information transfer need not be due to deliberate measurement. Any information transfer that does not perturb outcome states will abide by this rule. So in other words, pointer states, predictability, decoherence, etc., and what we will talk hopefully next time, quantum Darwinism, all are affected by this, or all are justified differently without appeal to Born's rule. Right. By the way, an important thing to notice, and let me go back, now let me not go back to the previous transparency. I think you remember, I've spent enough time on it. I have never appealed to probabilities there. The only two values of the scalar product were, whether it's 0 or not 0, or 1. There was no question of probability at all. Right? So the whole thing has no reliance on Born's rule whatsoever. Again, we shall switch gears because now we have distinguishable events. So we shall go on to try to get the probabilities. Right? So that's the next chapter. So again, if there are urgent questions, even not urgent questions, do not hesitate. Serge.
When you talk about mixed states here, don't you need to have some probability? What do you call a mixed state?
So this is a touchy question, but in quantum mechanics, you can talk about states which are entangled with something else without necessarily taking traces. Right? This is a so-called purification procedure. So if you restrict your reasonings at that carry them at that level, you will still arrive at the conclusion. But it's, at that point, algebra becomes painful. It's not what I had on the previous slide. If there are no further questions, let us proceed. Back to the plan. Derive controversial axioms, or as much of them as we can, from our credo 0 through 3. Why measurement outcomes are limited to an orthogonal subset, and why does Born rule yield probabilities? We got this, right? So we have the right to ask about probabilities of events. So let's do that. We have events. Now we are up to this. Now, a historical note. Couple of pages from a translation of the paper by Max Born, which introduced Born's rule. Paper has appeared in 1926. The translation appears in the book that Serge mentioned. Paper is five pages long. It's on the mechanics of collisions. So he was considering electron hitting an atom and scattering and trying to connect the wave function that describes the process with what detectors are seeing, right? So page number 1, an interesting note on the bottom. This paper was originally intended for the Naturwissenschaften, which was like, I think, Nature or Physical Review Letters at the time, a high-level journal, but could not be accepted there for lack of space. Got turned down by the editors, or the referees. Nobel Prize, quarter century later. Sorry?
The statement was certainly correct.
Yeah. So we go now to second page, and I've enlarged the part where probabilities and their connection with the amplitude is considered. And so we read, if one translates this result into terms of particles, only one interpretation is possible. Psi, where psi is the amplitude, gives the probability for the electron arriving, blah, blah, blah. Now, wait a second. Psi gives the probability? Oh, but there is another footnote. Let's check what it is. Addition and proof. More careful consideration shows that the probability is proportional to the square of the quantity psi. Again, Nobel Prize, quarter century later. So doing proofs is an important task for an author.
You need another note. It's not the square, it's the square of the modulus.
I'm not going to be nitpicky. Nobel Prize is a foregone conclusion. So absolutely. So how do we get there? Roots of probability actually go to France. It's one of the first examples of funding in science, in basic sciences. French aristocrats played cards, games of chance, and so on, and they were very bad at it. So they enlisted help of French mathematicians who were very good to teach them how to bet. I'm skipping details, Bernoulli's had their hand and so on, but the first successful theory of probability was codified by Laplace in a famous treatise which really wasn't accepted for good reasons. And one of the reasons I'm going to point out, right? So games of chance, 2 cards. I know for sure that one and only one of them is spade. Laplace says, and that's a basis of his theory of probability, that symmetry can be used to get at probabilities. The symmetry has to do with the fact that if I shuffle cards, this shuffling doesn't change my preference for which card I draw. If this is a situation, then the probability of me drawing a spade is 1/2, right? Now, this is sort of uncomfortable because probability doesn't have to do with cards. It has to do with me, with my ignorance. That's certainly part of the truth, but we know that if we looked at the same cards from under the table, shuffling would have a real physical effect. It would change the order. So this is why probability was thought, and philosophers still think of it as something which is purely subjective. And within classical physics, since Laplace, no one has invented a better way of talking about it. Amazingly enough, in quantum mechanics, the nature of quantum states offers a way which allows one to take Laplace's intuition but make it into something rigorous. Let me think about states of quantum cards. I have two tables, entanglement, intrication, sorry for pronunciation. One card is in a superposition of heart and spade on table S. And another table, very far, possibly, Lake Le Mans, as Nicolas Gisin did, there is another card in superposition of diamond and club. Right? This is an entangled quantum state of two systems. Now I'm going to do what Laplace suggests, shuffle. I shuffle cards on table S. I shuffled them. This state is an entangled state which is orthogonal, completely different from this quantum state. Right? So I took cards on table S, did this. This would exchange probabilities in particular. But now I can restore the state of the whole without touching table S. How do I do that? I shuffle cards on table E. Lo and behold, what ends up on the bottom is exactly the same what was there to begin with. So what happened is, on one hand, I know I've shuffled the probabilities on table S. On the other hand, I've restored the state of the whole without touching table S. So probabilities must be exchanged and yet unchanged. The only value of probability for which this is true is when they are equal. Let's introduce a slightly more respectable notation. And let's talk about it as a bona fide symmetry, because it is. I call it entanglement-assisted invariance, or invariance for short. I consider a composite quantum object consisting of a system and the environment. It could be Alice and Bob, whatever. When the combined state of the two can be transformed by a transformation which acts only on S, does nothing to E, but it can be restored to the initial state by a transformation that does nothing on S, but acts only on E, then this state is invariant with respect to this transformation. So in other words, I have this state, US acts on it, it does something, this and this are different, but then I come up with UE and act on it, the other end, causally disconnected, table behind Jupiter or somewhere, and the whole thing is the same. The whole thing is restored, therefore probabilities and everything else must be restored. So invariance is a property of this transformation and the state of two systems. One thing that invariance gives us is, in a way, decoherence without the need to do a tracing and using density matrices. How does it do it? Suppose I have a state like I had after the system interacted with the environment. A set of complex coefficients, a set of states of the system, and a set of states of the environment. These and these are orthogonal. This is so-called Schmidt decomposition. If you don't know what it is, don't worry about it. Bottom line is, when I have a pure state of two systems, I can always write it in a way which abides by these constraints. Now, unitary transformations with Schmidt eigenstates, which is transformations which rotate phases of these coefficients, alpha, just by acting on system S, are invariant. Why? Well, it's sort of obvious, right? I can rotate, oops, what do I do? I rotate these coefficients forward phi k, each of them. But now I can come up with a transformation which goes in the opposite direction and rotates them minus phi k. I don't touch system. I do it at the other end, at the environment. As a result, I can see that phases in an entangled state are not a property of a local system, so they can have no physical significance locally. So in a word, I'm getting locally Schmidt phases do not matter. Phases which do not matter means superpositions, coherence is lost, means decoherence. No traces, no Born's rule, no nothing. That was easy. Let's do something more ambitious. But let me start with a very simple case. Coefficients have the same absolute values. Phases are here just for show. We know they don't matter anymore, right? And I'm not going to worry about overall normalization. I'm going to worry about relative probabilities. The number of terms in the sum will matter. What I'm going to consider is a swap. Again, don't worry about the phase. I'm simply going to take a partner of EL and put it in a position EK. So I swap SK with SL. And it is clear that when the coefficients are equal, this swap can be undone by a counter swap. I take the two partners in the environment and I do the same with them as I did, or analogous thing with them as I did with the system. In other words, in a different notation, it is this, precisely this transformation. So what's my conclusion? My conclusion is that if I have a state in which coefficients differ only by phases, then probabilities of all the outcomes must be equal. And by normalization, if I insist that probability altogether is equal to 1, they must be equal to 1 over n. Now, it is Born's rule, but in a sort of very limited setting. But actually, it's a key, because we have derived purely on the basis of symmetry, without any frequencies, anything, any hand-waving, equality of probabilities. Equality of probabilities was enough for Laplace, but he had to postulate it on a basis of someone's ignorance. Here, it is not someone's ignorance. You, in fact, know exactly, or you can know exactly the state of the whole. It's a fact that knowledge of the state of the whole precludes you, essentially by Heisenberg uncertainty, from knowing anything about the state of either of the partners. So we have the simple result, the one I claim is crucial. Now we want to extend it. The rest is algebra. I don't know how easy it's going to be to absorb it from the audience, but let me show it to you starting with a simple case. So, special case with unequal coefficients. I consider a system which has two states, 0 and 2. I consider an environment which has at least 3 states, 0, 1, and 2. And the state plus is a superposition of states 0 and 1 in the environment. The system is always to the left. The environment is always next to it. I'm going to start with a state, entangled state of the system in the environment. I've chosen the coefficient so that this is square root of 2 bigger than this. I want to know the probability of 0 and probability of 2 in the system. I'm going now to reduce this state with unequal coefficients to a state with equal coefficients so I can appeal to what I've just achieved before. How do I do that? I'm going to attach an auxiliary environment E prime and let it interact with the environment E. So I start with my initial state here. Environment E prime in an initial state 0. And the interaction which carries out an operation known as controlled knot, or C knot. In other words, 0, 0 remains 0, 0, 1, 0 goes to 1, 1, and a slight generalization, 2, 0 goes into 2, 2. This is perfectly legal. Serge described in the previous talk implementations of it for the case of 2 logical states. I'm just generalizing to 3. So if this is legal, then 0 interacting with a superposition of 0 and 1 is going to give me, as prescription says, 0, 0 plus 1, 1. Now, there was a normalization here, square root of 2, which I carried out, pulled out from the whole thing. At this point, what I can do is simplify. It's the only algebraic operation of note. This square root of 2 and this square root of 2 disappear. What I'm left with is a state which has 0, 0, 0, 1, and 2, 2, all of them with the same coefficient. So I have now 3 orthogonal possibilities. Here, if I tried to do my trick of swapping, I would have failed, because if I swap 0 and 2 and then swap plus and minus, the place of the coefficient with respect to the state would change. It would be a different state. However, here, I can swap 0, 0 with 0, 1 at will and make it up for it by swapping 1 with 0. Same here, 0, 1 with 2, 2, and I can swap 2 and 1. So I know probabilities of 0, 0, 0, 1, and 2, 2 must be equal. Now, clearly, each of them, by symmetry, has to have probability of 1/3. Consequently, probability of 2 alone, there's just one of them here, is 1/3. Probability of 0 is a complement, 2/3. So we have Born's rule. Amplitudes got magically squared. By counting, not by counting outcomes, by counting possibilities. So this is very much what Laplace suggested. And by proving symmetry. So we have Born's rule. Of course, one can extend this. Oh, there was no need to assume additivity in the process of probabilities. All I needed to say is that they should sum to 1, or to whatever normalization I had. So I have Born's rule. I'm not going to torture you with this. I think you can probably see how to extend what I did before to any situation where the coefficients, where the coefficients are commensurate. If not, Physics Today from last October has that. And in general, for this case, you get probabilities which are proportional to squares of the amplitudes. This is for commensurate probabilities. Now one could question of whether it's possible to have non-commensurate probabilities. I'm not going to think about this event. I'm going to say something else. I do want to assume continuity. So in that case, whatever incommensurate situations I'm going to find myself into, I can do a Dedekind cut or whatever these things are called and prove to myself that probability has to be still given by Born's rule. So I think it's a good time to wind down. This summary focuses on what I went through today, and I particular on what I did in the last part of the talk. New symmetry and variance of joint states of quantum systems. It is related to causality. In quantum physics, perfect knowledge of the whole may imply complete ignorance of the past. This is, in fact, how we have derived probabilities. This possibility doesn't exist classically. Classically, imagine, two coins, one here, €1, €2 coins. You flip one of them, which is a swap operation. There is no way you can restore the state of the whole by flipping the other one. In quantum mechanics, you can do that. The reason for that is that Cartesian products of states of individual systems give you a state of the whole in classical physics. If you know the state of the whole, that means you know the state of each piece. In quantum mechanics, tensor products plays a key role. And in that situation, it is possible to know the state of the whole and be, as a result, completely ignorant of the state of the parts. Born rule follows as a consequence. Relative frequency of interpretation of probabilities naturally follows. I have not derived it, but it's in my papers, and you're welcome to visit that. And variance supplies a new foundation for everything, including decoherence. So next time when we talk about decoherence, and we'll start with decoherence again, it will be legal. We have reduced the list of postulates down to quantum credo with a bit of a question mark hovering over 4b, which was a collapse. And I think that's a good place to stop. Thank you so much.